All right. So we have basically we have solved the question using the recursion. Now we're going to optimize this a little bit. Okay. Now, if you notice, when we were solving for f of 3, right, we were we went to f of 2 to f of 1 to f of 0, f of negative 1, f of 0, f of 1, f of 0, and f of negative 1. If you look at this recursion tree very closely, you will find that there are a lot of function calls which are being repeated. For example, here, for example, here, for example, here. And if you would start with like some, say, a bigger recursion tree, so for example, f of 5, f of 4, f of 3, f of 2, f of 1, f of 0, f of 0, f of negative 1, f of 2, oh sorry, this would be 1, and then f of 0, f of negative 1, then you'll go to here, then f of 1. You can see that as to how many times f of 1 is being called, and then over here more function of f of 1 will be called, and you can see over here f of 2 was called here and over here. So what if what we could do is that when we're computing this f of 1 over here, we can compute this result, and then when we reach to this f of 1, we can use the computed value, so we don't actually need to solve this again. Okay, what if I can save the value of function f of 2, so that from over here, so that when I need to recompute f of 2, I can use that stored value and I don't need to go in this entire depth of the tree. Now, for people who don't actually know as to how recursion calls are being executed, so for example, if you write jump once first, this will be as um, n as, sorry, f of n minus 1, and then you write jump twice. This basically means f of n minus 2. So since jump once is written first, this will become your left subtree, which is this whole path. And since you wrote this thing as the instruction after it, then it will become your jump twice as your right subtree. So first it's going to solve the entire left subtree, then go to the right tree, then go to the right tree, and then go to its entire left depth, come back, then to the right, and so on and so forth. Okay, so this is for people who actually don't know as to how recursion calls are being executed. So very quick reminder. Okay, so how are we going to do this? How are we going to store values? This is where the concept of dynamic programming comes into play. So we can solve this problem in two different ways, which is by memoization and by tabulation. So first we're going to look at memoization. Memoization is very easy. It comes from the word of memory. So we're going to solve this using memoization. What are the steps of memoization? Let me write that down so it's easier for you to follow along. So the first step is, one second, let me just wear my glove. Okay, my glove is here. Okay, so the first step is you need to initialize dp array. Normally you can also use hash table, but I like to use dp arrays. So initialize an array which I've called dp, so I like to call this dp array, um, with or of size n with value -1. The second step is um, save the base case values in DP array. The third thing is, once you've saved the values in the DP array, you're going to check if DP, whichever n that is, if that does not equals to -1, return DP of n. If not, then compute the sub problem, which is normally a recursion, and store that in dB of n. Okay, so let me explain as to what this basically means. Okay, before I proceed, I want to tell you something. Um, if you look over here closely, okay, um, or let me create another recursion tree for you to help you understand this concept. Okay, so um, let's think about this. Okay, um, over here, if you will see, the problem will always ask you for n is greater than equals to 1 and n is lesser than equals to 30. Okay, um, what I'm trying to say is that the base case that I told you earlier, where I was saying that if n double equals to 0 and n double equals to, if n is lesser, if n is double equals to 0, then return 1, that you found a way. And if n equals to -1, you want to return 0. Okay, this is also fine. Another way as to how somebody can think of the base cases is that, what if I think about sub problems? Okay, what if I say that if I was given one stair, then I know that there's only one way to reach this staircase. So I know this is going to be 1. Okay, so I'll write this down. If n equals to 1, return 1. There is one way to reach this place. If there are two staircases, then I know for a fact that there are two ways to reach this, which was mentioned over here. So if n is 2, I know that there will be always two cases. Why am I saying this? Because when you use this base condition instead, what you end up doing is that you end up basically um, you end up uh, what you end up doing is that you don't need to compute these things anymore, right? You don't need to compute f of 0 and f of 1. These are unnecessary computations, because you will never find the need to go to that depth. Because if you look at f of 4, which is an even number, you will always end up at either f of 2 or f of 1. Okay, if you are using f of 5, you will either end up at f of 2 or f of 1. Always, always, always. You will always end up at either f of 2 or f of 1. You can split this more, and when you split them, then you will get 0 and -1. But this is like a small optimization trick which you are doing, and this will actually help us out when we're trying to construct this. So what we've done is we've just improved our base case a little bit. Okay, I hope that you could understand this. What I'll repeat again. This is just telling you the solutions of the sub problem. For example, if I'm over here, I know for a fact that there is only one way to solve this. If I'm over here, I know for a fact there are two ways to solve this. if I'm over here, I know that there is one way to solve this. I add both of them and I get 3, which is that if I'm at f of 3, there are 3 ways to solve this problem. Okay, so okay, so now I'm going to write this entire memorization very quickly. So let's start with the first one, initialize DP array. Okay, I'm going to be writing the Python code. So let's say that we are trying to solve for f of 4. Okay, so we are going to be needing an array of size 4. So we are going to start with 0, 1, 2, 3, 4, and each of this is basically donating the solution of the subproblem. So this index 1 is denoting the solution of f of 1. This is denoting the solution of subproblem f of 2, and so on and so forth. This is going to be my DP array, and I am going to initialize all of this with -1. How am I going to do this? In code, this will be just DP, or let me just add a colon instead so that you don't get confused. So dp will equals to -1 times n plus 1. Why did we do n plus 1? Because if we look over here, we have 5 elements because of the 0. This is the reason why we are doing n plus 1. Okay, then next, so we have done this part. The second part is save the base case values in the DP array. Okay, so we're going to save these values. So the DP1, this base case, we're going to save this. So we know that DP1 is equals to what? It's equals to 1. We're done with this. Okay, DP2, which is this base case, what is it equal to? It's equals to 2. We have done this. So we have saved the base case values in the DP array. Okay, now we will have our original code which we had earlier, which was jump once will be equals to um, function n minus 1. We had the other one which was jump twice for f of n minus 2. We are first of all going to check um, is our dp n does not equals to negative 1, which means that do we actually have the solution of this of the sub problem. If we do have the solution to this problem, return the answer. If we don't have the solution to this sub problem, store that into dpn. So jump once plus jump twice and then return dpn. This is all you did. So that is basically memorization. So let me just code this up very quickly for you. So we are first of all going to come here and we are going to define another function, a helper function, to help us out. So we're going to have self n, and we are going to have our db array over here. We are first of all going to say that if I, or if n is lesser than equals to 2, then return n. This is basically for like edge cases. If like the question gives you like n as 1 or n as 2, you just want to return the answer. Okay, so we're going to initialize our dp array. How did we do that? -1 list times n plus 1, and then what we did was we um, were storing the values of our base cases. So we have saved our values. Now we're going to return self.helper n comma dp. We're going to go inside this dp function and we're going to define our recurrence relationship. So what is this? Self.helper n minus 1 comma dp jump twice as self.helper n minus 2 comma dp, and then over here we're going to say that if n if dp of n is not equal to -1, which means we actually have the answer, then just return this. Then we are going to store the answer. If not, so dpn equals to jump once plus jump twice, return dp of n. And as a result, it is working. You can submit this and it will work fine. I have already submitted this, so I don't find the need to submit it again. Okay, so this was the submissions, the same thing which I've done over here. Okay, so next move to the next part, which is now to solve this using tabulation. What is tabulation? Let me just wear my glove again and then I'll start. So tabulation is bottom up. So let me bring this back up. So over here we were coming top down, which was starting from f of 4, we were going to our base condition. This is basically top down because we're coming from the top to the bottom. The other one is bottom up, in which we are now going to go from the bottom to up. Okay, so for this I am going to need my dp array. I'm going to need my dp array, and other than that I don't need anything else. Okay, now in tabulation, normally what happens is that you're trying to solve this using a for loop, and normally, okay, also another thing, you can only apply tabulation or memoization or dynamic programming. Whenever you're going to say dynamic programming, it includes both tabulation and memoization. You will always use dynamic programming when you have overlapping subproblems. What were the overlapping subproblems? Where I was saying that you need to recompute subproblems, right? That is called overlapping subproblems. Okay, so for tabulation, you're mostly using for loop, and over here, if you look at this array, we know that this is the solution of f of 0. We know this is the solution of f of 1, and so on and so forth. So we need to move from here to here. Okay, also if you note very carefully, um, we are actually for tabulation or for this problem, if you notice, if we are trying to compute f of 3, which is this thing, right, and we know for a fact that f of 1 is 1 and this is 2. Okay, we know this. Okay, when we are solving f of 3, we are going to be computing f of 2 and f of 1, right? If we are computing f of 4, we are computing f of 3 and f of 2. If we are computing f of 5, we are computing f of 4 and f of 3, which basically means is that this is kind of like um, it's kind of like um, Fibonacci series, where you need the last two elements. So if I want to calculate f of 3, I need the result of f of 2 plus the result of f of 1, and that you are going to store that over here. So this will become your this will become plus 3. If you want to compute f of 4, we are going to use this thing and this thing, add them both up, and we are going to get plus 5. So this is what we are going to now do. So let me just reset this, or I can use this code. I don't need the helper function anymore. I can do this within this function. So I already know the answer for 1 and 2. So we are going to start our for loop for I in range 3 comma n plus 1, and let me come back. So in for loop, what we are going to do is, if we want to compute f of 4, okay, so let me go back a little bit. If you want to compute this f of 4, we need f of 3, right? So let's start from over here, and let's say that this is our I. This is our pointer I. Okay, if you want to compute dp of I, what do we need? We need this thing, which is dp of I minus 1. And what do we need? We need this. We need dp of I minus 2. That is all we need. So we are going to do this. So I'll just say that my jump once is basically dp of I minus 1. My jump twice is basically dp I minus 2. dp I minus 2. If I want dp of I, that will be just jump once plus jump twice. And then once we are complete, we just need to return dp of n. We don't actually need this. And as a result, this is also working. Now I want you to notice something very, very carefully. The reason as to why I opened up this solution over here is because this was the memoization. Okay, and if you notice very, very carefully, um, you will find something very similar. The recurrence relationship is the same. Jump once, n minus 1, jump once, and I minus 1. Jump twice, n minus 2, jump twice, I minus 2. dp of n equals to jump once plus jump twice. dp of I equals to jump once plus jump twice. Which basically means is that you will find the similarity that once you have solved your problem using um, recursion, your 80% of the problem is complete. You optimize that using memoization, another like 10-15% is complete. And then if you want to do that using tabulation, you will see that the dynamic array is sometimes similar. So constructing the solution for tabulation is very, very easy once you can figure out as to how you can solve your recursion and memoization. It doesn't work all the time, but it works sometimes. Okay, so that was your climbing stairs problem. Now we're going to look at an even much difficult variation. It's just slightly difficult, not that difficult, but we're going to look into that next.